Let's start. I welcome you all to IT446 lecture, virtual lecture, and let's start. Let me share the slides. Okay, I hope that you guys can see the slides. There are not many students in the class. Why? Okay, so we'll have a this lecture is also not very long, so we'll have a we'll try to finish it, and then I've already uploaded the slides. You can also download the slides and see about the lecture. Okay, so now this lecture is about also clustering, and it has some advanced topics in clustering. Okay, so we'll study about model-based clustering, clustering high-dimensional data, and clustering graphs, and network data, and clustering with constraints. So the first one is fuzzy set or fuzzy clustering. In this method, we make some fuzzy clusters which are based on probabilistic based models, and even in previous methods, every data object is assigned as exactly one cluster. But as you know that the fuzzy rules or fuzzification, it tells us, it fuzzifies the thing, and it will inform. It is not hard clustering method. Okay, it's like a soft clustering method, and we can partition the data into some fuzzy sets, and for each fuzzy set we find the fuzzification value or degree of fuzziness. So it's a mixture model which assumes that a set of observed objects is a mixture of instances from multiple probabilistic clusters, and conceptually each observed data object is generated independently. Now our task is to infer a set of k probabilistic clusters that is most likely to generate D using the above generation diagram. So a set C of k probabilistic clusters with probability function f1 to k, it has a probability of omega 1 to k, omega k. So the probability is given by the following equation, as you can see in the slides. So we follow the expectation maximization algorithm, which is also known as the EM algorithm. It has an expectation step and a maximization step. So in expectation step or E step, we have a given cluster centers, and each object is assigned to the cluster whose center is closest to the object. In maximization step, we have a given cluster assignment. For each cluster, the algorithm adjusts the center so that the sum of the distance from the objects assigned to this cluster and the new cluster is minimized. There are strengths and weaknesses of these. The strength is that the mixture model are more general than partitioning and fuzzy clustering, and the clusters can be characterized by a small number of parameters, and the results may satisfy the statistical assumption of the generative models. The weakness, on the other hand, of this model is that it can converge to local optimum, which means that it can trap in local optimum instead of a global optimum, and it is computationally expensive if the number of distributions is large, and it also needs a large data set, and it is hard to estimate the number of clusters through this algorithm. The next type of algorithm is known as clustering with high dimensional data. We know that high dimensional data means that we have higher dimensions, higher number of attributes. So this has many applications, for example, in DNA microarray data and text documents. And the major challenges are that there are many irrelevant dimensions, and these may not be the distinctive dimensions of the cluster. and distance measures becomes meaningless due to some equidistance properties, and cluster may exist only in some subspaces. So there are many methods, for example, subspace clustering, where we search for clusters existing in subspaces of the given higher dimensional data space, like click and process methods. And then another method is that we reduce the dimensions using a dimensionality reduction technique. In this, we construct a much lower dimensional space and search for clusters there. So traditional distance measures can be dominated by noises in many dimensions. So traditional distances are not adequate data when we are talking about higher dimensions. And we have been discussing about this problem of the curse of dimensionality. We know that data in one dimension is relatively packed, and adding a dimension will stretch through the points across the dimension, which will make it further apart. And if they are further apart, then we can easily distinguish between one cluster and another cluster. Here you can see graphically how it works. Okay, so in subspacing, subspace clustering method, we have a subspace search method where we search various subspaces to find clusters. It has a bottom-up approach and it can have a top-down approach. So correlation-based clustering methods can also be used, and by-clustering methods, which are optimization-based or enumeration-based, they can also be used. So for bottom-up approach, we start from the low dimensional subspace and search till high dimensional subspaces. Only when there are many, there may be clusters in such subspaces. And various pruning techniques can be used to reduce the number of high dimensions. And in top-down approach, we start from full space and search smaller subspaces. So effective only in the locality assumption, and restricts that the subspace of a cluster can be determined by the local neighborhoods. An example is Proclus, and where we use the k-meteoroid-like method. Okay, so dimensionality reduction, in some situations it is more effective to construct a new space instead of using some subspaces of the original data. So to cluster the points in the right figure, any subspace of the original one cannot help, since all the three clusters will be projected into the overlapping areas in X and Y. So we construct a new dimension, take it to another dimension. As you can see, the Z dimension, which is the dashed line, and by this we can classify in the subspace. Okay, the next topic is about clustering graphs and network data. Graph is a very important part in clustering, and it has many applications. For example, bipartite graphs in customers and products, authors and conferences. As an example, web search engine, they can be represented in the form of a graph, where we have click-through graphs and web graphs. Then we can also construct graphs for social networks, friendship and co-author graphs. Okay, so there could be different similarity measures which we can use for graphs. The first one is geodesic distance, and then distance based on random walk, or SimRanks also it is called. And so graph clustering methods include minimum cuts and density-based clustering. If, for example, fast modularity and Closet, Newman, and scan algorithms. Excuse me. So what is a geodesic distance in a graph? So a geodesic distance between 2 points A and B is the number of edges of the shortest path between A and B. And it has eccentricity, and eccentricity of V is the largest geodesic distance between V and any other vertex in this graph. A radius of a graph G is the minimum eccentricity of all the vertices, and the distance between the most central point and the farthest border is known as the radius. Now what is the diameter? Diameter is the maximum eccentricity of all the vertices. And then we have peripheral vertex. Peripheral vertex is a vertex that achieves the diameter. And here are some examples, some mathematical expressions. You can go through these expressions. We have an expression for sparsity of the graph, and okay, so there are many challenges in finding good curves in graphs. For example, high computational cost is one of the challenge. Then there are maybe sophisticated graphs which may involve weights or cycles. Then there can be some very high dimensional data inside the graph. A graph can have many vertices. It can also have high sparsity, where a large graph is often sparse, meaning each vertex on average connects to only a small number of other vertices. So we have two approaches for graph clustering. We can have generic clustering methods and designed specifically for clustering graphs and these methods. So for clustering high dimensional data, we extract a similarity matrix from a graph and use a generic clustering method that can be applied to the similarity matrix. For example, could be spectral clustering, and there are many methods, for example, SCAN, which stands for Structural Clustering Algorithm for Networks. So SCAN is a density-based clustering for network, and we can find how many clusters are there, what size they should be, what is the best partitioning, and they should some points be segregated. You can see an example network. So the application could be given simply information of who is associated with whom in a social network, and it could identify clusters of individuals with a common interest or special relationships, families, colleagues, or other things. So social network model has cliques, hubs, and outliers. So individual in the tight social group or a clique know many of the same people regardless of the size of the group, and individuals who are hubs, so they know many people in different groups but belong to no single group. And for example, politicians, for example, they may bridge multiple groups. And then we have outliers, which are individuals who reside at the margin of the society. For example, hermits, I know very few people. Now the neighborhood of a vertex is defined as the immediate neighborhood of a vertex. The last topic for this week is clustering with constraints, and why constraints-based clustering analysis, because we need a user feedback and less parameters but more user-desired constraints are there. So handling hard constraints is strictly respect to the constraints in cluster assignment. You have to follow them. Then there are some soft constraints where we can penalize, and when a clustering violates a soft constraint, a penalty is imposed on the clustering, and overall objective is to optimize and the clustering quality and minimize the constraint violation penalty. So objective function over here is the sum of distance and used with the constraint violation penalties. So we can add it in the penalty and then you can compute the objective function. Okay, then there are some user-guided clustering which has some special kind of constraints, and on each level user can control the constraints by giving the values. So it can be semi-supervised clustering where user provides a training set consisting of similar and dissimilar pair of objects. and some of these sets are provided by the user, some are there in the data. So much information is needed to judge whether two tuples are similar. So a user may not be able to provide a good training set, and it is much easier for a user to specify an attribute as a hint. So that's why we will not use semi-supervised most of the time, and we'll stick to the supervised learning. Okay, so this concludes the topic for this week. If you notice on the Blackboard, I have uploaded the two slides, all the modified slides on the Blackboard. You can go through these slides, and if you have any problem, you may ask your questions over here. You can raise your queries over here. Take some time and go through the slides for this week. And with this, we have covered the material till week number 13. Okay, so next week, inshallah, we will be covering the material for the next week, for week number 14, sorry.